Alright, so today's talk is about electrochemistry. This is part one of a multi-part series on electrochemistry. You can find them all on my YouTube channel. And today what we really want to start off with is a little bit of the review of things you should have learned in General Chemistry 1, such as Leo the line goes grr, kind of a mnemonic to understand which species is being oxidized and which is being reduced. The concept of calculating the oxidation number to track which species is being oxidized or reduced. Comparing oxidation and reduction, the verbs, as well as the names oxidizing agent, reducing agent, oxidant, and reductant. Understand the concept of a half reaction and how that pertains to the overall reaction, and how an overall reaction can help you understand the electron balance of a half reaction. To know the difference between voltaic cells and electrolytic cells, know the components of a cell, know the function of a salt bridge, know voltaic cell notation, and then finally how to qualitatively read a standard half cell table. So let's begin with a little review of redox. We're going to start off with the metals reacting with an acid to make a salt and release hydrogen gas. You may have studied this in General Chemistry 1 under acid-base reactions, but it also is a redox reaction. And in order to review that, we might draw the oxidation numbers above the species and see who's oxidized and who's reduced. So reminder that elements and pure metals are oxidation number 0. Hydrogen gets priority in a compound as +1, and then the anion beside it will balance out, so the overall compound has a net charge of 0. So chloride is also -1. Zinc and the zinc chloride, this is an ionic compound, so you basically take the ionic charge, and that is its oxidation number. So zinc is +2, chloride is -1, and then hydrogen is elemental state. Diatomics count for that, so hydrogen, nitrogen, oxygen, and fluorine. Those also would have that elemental state, so oxidation number of 0. And once you see that, using that mnemonic Leo, that if you lose an electron you're oxidized, that zinc lost 2 electrons, so it was oxidized. And just a reminder for definitions that this was a verb, it was oxidized, so consequently it's referred to, or the name for it, or the noun, is a reducing agent or reductant. And one way to remember the difference there is that when something undergoes oxidation, it can cause something else to be reduced. So something that undergoes oxidation is referred to as a reducing agent or a reductant. And if you look at the oxidation numbers, you can also see that hydrogen gained an electron, so it was reduced. So it underwent reduction, so consequently it causes something else to be oxidized, so it's referred to as an oxidizing agent or an oxidant. Another important thing here, and this will be really stressed a lot in electrochemistry, is that oxidation and reduction don't happen in a vacuum. They don't happen alone. They're driven by each other. So if somebody's losing electrons, some other species is gaining electrons, and vice versa. And for every electron that's gained in reduction, there's the same number of electrons lost in oxidation. So whenever you sum up electrons in this reaction as drawn, there were actually 2 electrons lost in oxidation, and those 2 electrons were also gained in reduction. Now, on occasion you have something that's just a counterion to get the ionic charge to 0 of species that really do nothing. So if you look up here, the chloride ion started off at oxidation number -1. It ended up in the products as oxidation -1. So in essence, it's a spectator ion. As you get into electrochemistry, though, it's important to know that counterions have an important role. One of them is to charge balance the solution. It's as we've learned in thermodynamics in the last section, it's very improbable that you're going to just start building up positive charge in a solution or building up negative charge. That would require free energy from another source in order to do that. So spontaneously things will drain down to net charge 0. So the spectator ions are going to be important, although a lot of times they're not written in equations. They're just assumed because it doesn't really matter what spectator ions in there. This could have been chloride, it could have been bromide, it could have been iodide. A little caveat on that though is coordinate covalent complexes, metal complexes that literally are covalently bound to anions, that totally changes the electrochemistry of that particular material. So it will lose or gain electrons at a different potential than it did before. So that's kind of the caveat of that. But that's just a few comments on spectator ions. Electrochemistry really depends on redox chemistry, so that's the key. And so in the big picture view, there's really two things to look at there, and that's the spontaneous reactions, harvesting the free energy off of a spontaneous reaction, and the non-spontaneous reaction, where you have to drive that reaction by pumping free energy obtained from another source into it. So those are two general categories that you need to be familiar with. So let's start with the spontaneous reaction. Let me just show you how we know it's spontaneous, going back to our thermochemistry chapter, and I look at this reaction where copper ions interact with zinc metal and you make zinc ions and copper metal. The question would be, is that spontaneous or not? Well, let's look at the free energy. And if you go to the standard thermodynamic tables, look up your numbers, you see that the copper 2 ion at standard conditions, 298 K, or 66 kilojoules per mole. Zinc solid has 0, as do all the elements off the table. Zinc 2 plus has minus 110 kilojoules per mole of free energy, and the copper solid product also has 0 kilojoules for free energy. So remember that what you do is you take products minus reactants, so the free energy of the two change sign, so we change those, then we just sum across there and you get minus 166 kilojoules per mole of free energy per mole of every copper 2 cation that converts to copper. And so we see there's actually, at standard conditions, and remember again that that would mean that the concentration of the solutions was at 1 molar, and it's at 298 K, then at those conditions this reaction would actually have minus 166 kilojoules per mole that could be harvested from that. And the fact that it's a negative sign means it's a spontaneous reaction. We think of these reactions happening in the same container, but a lot of times in electrochemistry, but not always, but a lot of times what you do is you separate the reactions into two separate containers and then just connect them with a conductive circuit or wire. And so if that was the case, you know, zinc is turning to zinc 2 plus, right? And if that's true, that's creating electrons, and those electrons could be picked up by the electrode, right? And they could travel along the wire, and meanwhile over here copper 2 plus is being reduced to copper, so it would utilize those same electrons. And this is basically an electrochemical circuit. And just a concept that might come out of here, I'm just going to give you 3 applications so you see why we study this. This is a concept, as is right here, of galvanization. In other words, spontaneously, given these conditions, zinc's going to go to zinc 2 plus, while copper, instead of going to 2 plus, it's going to go back to pure copper. So if you galvanized, in other words, if you coated zinc onto copper, and that means that the selective oxidation of zinc is going to occur first, and it's going to drive the copper 2 plus and keep it in copper. In other words, it's going to keep the metal metallic. The more active metal is going to be sacrificially oxidized. So that's just kind of one concept that deals with electrochemistry. Another one is corrosion. That is, for example, you put iron in the presence of oxygen, it turns to iron 3 plus. So you put iron in the presence of oxygen, it turns to iron 3 plus. And the oxygen started off at oxygen 0 and it ends up at oxygen 2 minus. So the oxygen is reduced, therefore it's an oxidant, and hence the use of oxidant in the name. And iron starts off at iron 0 and it changes to iron 3 plus, which is oxidation. But corrosion is related to this redox electrochemistry. And probably the most famous and the biggest application is, well, we have all this free energy, right? We have minus 166 kilojoules. What if we put something on the circuit to harvest those electrons flowing by? This is literally electricity. That's what electricity is in a wire, flowing electrons. And if those have free energy that you can tap into, you could turn on an appliance, in this case a light bulb. And so that is the fundamental concept behind a battery or a galvanic cell or a voltaic cell. So this is one thing you want to put in your notes right away, is that these three terms are really interchangeable. Most folks, most laymen, non-science types, will refer to things as batteries, but you'll hear them referred to as voltaic cells or galvanic cells, all the same thing. That basically you have a redox reaction that you've separated the two half reactions and you got it connected by a wire and you're able to harvest the free energy off that circuit. So all three of these categories refer to applications we've made with spontaneous redox reactions. So now what if we wanted to run it in reverse? How could we get it to go in reverse? And the answer to that is, we start with copper solid and zinc 2 plus and we run it in reverse, so consequently we know that the free energy for that is plus 166, which is not spontaneous. So in order to go in reverse, you've got to have another reaction taking place somewhere else that's creating free energy, and we tap into that to drive electrons. So for example, you might have coal burning in a coal-fired power plant, which is generating electricity, which creates an excess of electrons. And so if you had those electrons flowing from that circuit, i.e. you plug it into your wall socket, all right, the negative poles could actually drive electrons onto the zinc ion, making it turn to zinc plus. Well, consequently, that would mean that somewhere out here on the power on the other pole, you would have this loss of electrons, which would kind of create an electron sink, so you could start driving electrons away from this side over where the copper's trying to react. And that, the copper could actually undergo oxidation in this case. And the electrons that are generated would go into that sink from the power plant. So if you think about what's really going on here, without getting really caught up in all the chemistry going on at the power plant, you're in essence just taking the free energy being generated at the power plant to run a reaction in reverse, to run a non-spontaneous reaction. I just flipped over because I'm hoping as I'm teaching you science that you'll favor not using coal-fired power plants and think about alternative methods that don't also pollute so heavily. So solar panels could do the same thing. We could get the same reaction running with solar panels. The main thing is that we have the free energy of the sun driving this non-spontaneous reaction in reverse. But let's take a few applications of this. Why would we learn about this general category? Well, maybe you want to take your batteries that you learned about in the last section and you've ran them down, all the free energy's trickled out of them, and you want to recharge them. Well, you could plug them into the wall socket and harvest energy, in essence, from the sun, in this case, to get that free energy back so you could reuse the batteries. Electroplating is done where you take a metal such as gold ions and you place them. In this case, this is a picture of the Colorado State Capitol, and so you can spray thin layer of that gold ion onto there, and then with the little electrical charge put across there, you can actually plate the gold out in a very thin layer. We do a lot of electroplating. A lot of these nickel plated and silver plated handles or silverware, that sort of thing. That's, a lot of the inexpensive metallic looking features around your home that are used for decoration. Those are quite often electroplated. And remediation is another concept where, what if we were, in this particular case, we were taking zinc out of solution, and if that zinc was in solution, it would be possibly polluting the water, for example. And if you set up a circuit like this using the free energy of the sun, you could drive the zinc out of solution and back to zinc solid into a solid metallic condition, and it would be insoluble. So that's just some applications for electricity or electrochemistry, and I want you to think about, in general terms, electrochemistry is either the big spontaneous category or the non-spontaneous category, and we'll talk about all of these in the upcoming videos. So continuing on with the review, though, I want you to remember how to actually determine oxidation numbers. This is a General Chemistry 1 concept, but it's worth going back through again. And as you work down the table, we're going to be reminded that the first 3 priorities really deal with free elements or diatomics, elements as they're found in nature without being oxidized or reduced. Okay? These are all assigned the oxidation number 0. When you talk about ions, remember that whatever your ionic charge is, that is also your oxidation number. So for example, I've got iron 3 or iron 2 sulfate down here, and in this particular compound, the iron itself has an oxidation number of 2+, just like it has an ionic charge of 2+. And then when you get to the sulfate ion, you might want to know the actual oxidation numbers of the sulfur and the oxygen. So one of the keys to that is, whenever you have an ionic compound, just split it in half, and basically it says that, look, if you want to work out the charges of the sulfate ion, you want to know the sulfur and the oxygen. The starting point is that the net charge on this sulfate ion is actually a 2-, and that's going to be critical here in a minute, and I'll explain that. Hold on. Alright, so, and then there's kind of a dividing line I like to put on these rules, because this top part really deals with ionic compounds, and the bottom part deals with covalent compounds. And the keys here really are all of these charges. If you'll look at them, fluorines -1, hydrogens +1, oxygens -2, chlorine, bromine, iodine are -1. Those are really charges that are similar to what they prefer to take as ionic compounds. But when it comes to oxidation numbers, it has to do with priority. So it's important to remember FHO and remember it in that order. Fluorine comes before hydrogen, comes before oxygen, and for example, oxygen comes before sulfur. So for example, let's kind of work one of these through. Let's take the sulfate anion and just figure out the oxidation numbers of sulfur and oxygen. So what I like to do, following the rules, right, is I put things below, and I say, well, according to this next rule, it says that the sulfate overall charge is the same as this ionic charge, which is -2. And then let's start working back by priority. We have sulfur versus oxygen. Oxygen's next in priority. It gets assigned to -2, so that's done. Oxygen's -2. There's actually 4 oxygens in there. So to get to that net overall charge, what you got to do is you got to take each oxygen at -2 times the 4 that are in the compound, multiply them together, you get a -8. So now you're at this point of figuring out, okay, what charge, -8 gave me a -2 charge. The answer there is certainly 6. And then you work your way back up and say, well, how many sulfurs are in the compound? Right, and there's only one, so oxidation number on sulfur itself is 6. So if I was working out oxidation numbers within the sulfate anion, the oxygen is -2 as we would expect. The sulfur is actually a +6. And once again, doing these oxidation numbers alone is kind of an exercise, but you really want to do it for application. You have to look at an equation and figure out, well, starting at reactants, did the sulfur change oxidation numbers going to the product side, or did the oxygen start at -2 and by the time it got to the product side, did it change to something else? Because that will indicate whether there's redox that we can either harvest for a battery or, as we've talked about with the other examples. Print out these rules, or you might want to flip back, but here's a lot of chances for you to practice. So what you want to do is, let's just assign oxidation numbers to every element within every compound that's listed here. Stop the video, put down all your answers, and when you're ready to check your answers, you can restart the video. Okay, let's see how you did. Starting with here, chromium ends up at a +6, oxygen's -2. In water, the priority is hydrogen. 2 of those hydrogens give you a +2 charge, counterbalanced by a -2 oxygen, which consequently is what oxygen usually is assigned. But hydrogen peroxide shows you the counter example where the oxygen actually changes its oxidation number. And remember, once again, that's because hydrogen gets priority, and so the oxygen consequently would have to be a -1 to balance out the +2 hydrogen. This is a great example where you basically are needing to compare a chlorine, and fluorine gets the priority. Carbon's not even listed, so the first priority is fluorine at -1. The next priority is chlorine at in this case would also get -1. The remainder is carbon, which picks up the difference. In this case would be +4. This is an example where you go to your rules and see that although hydrogen is a priority, when you get into connecting it to boron, it actually gets a -1 charge as opposed to a +1 charge. And then here's another example still yet of where hydrogen gets priority, but when it's attached to a metal, it actually gets a -1 charge again. So this is potassium hydride. In this case, hydrogen is -1. Another example where between chlorine and fluorine gets priority at -1. Chlorine picks up the difference. Overall, there's no net charge on this, so it has to sum up to 0. So in this case, chlorine gets the +1. Don't be fooled by this little guy here, right? Because this is an elemental element or a diatomic, so it gets assigned 0, right? And then last but not least, we put sulfur in with oxygen, and oxygen gets the priority, -2. The difference then would have to be sulfur at +4, and this is different than the polyatomic ion that we had looked at earlier with the sulfate. This is the covalent compound sulfur dioxide. And let's kind of start drilling down on just kind of definitions of that we're going to need to talk about spontaneous reactions, i.e. voltaic cells or batteries, or also referred to as galvanic cells. So here we have a simple battery setup where we're going to run a zinc 2+ couple on one side, and on the other side we're going to use a copper 2+ couple. And notice how we lay this out. We put the metal, dip it down into a zinc solution, and we take the copper and dip it into the copper solution. Now the thing that's not written in here that has to be assumed is there's a counter ion. In other words, zinc 2+ isn't alone in a vacuum. It's zinc 2+, maybe sulfate or 2 chlorides. And by the same token, copper 2+ is the same. Sometimes we leave those out just for to avoid things get cluttered. So on the oxidation side, zinc is turning to zinc 2+, and so that's called a half reaction. That didn't happen by itself unless there was an exchange of electrons. But to help us understand batteries, sometimes we use these half reactions. On the reduction side, the half reaction is the copper 2 plus reducing down to copper solid. And another definition for half reactions is basically the oxidation and reduction reactions that create one half of the battery. In other words, that creates the cathode or the anode. But anyway, if you'll combine these half reactions together and you balance out the electrons so that there isn't more electrons created in oxidation than those consumed in reduction, then when you cancel like species, you get the overall reaction. That is the difference between a half reaction and an overall reaction. Whenever zinc undergoes oxidation, it creates electrons, so that therefore makes this plate electrically negative because there's a buildup of electrons, and then those electrons can then flow across the circuit over to the where there's a positive buildup due to reduction. So these little plates that transfer the electrons, those are called electrodes. That's where electrons are transferred into the circuit from the redox reaction. And after running the reaction for a while, you would notice something. In the zinc half reaction, you see that zinc is going to zinc 2 plus, it's going off into the solution, so over time the zinc bar would start to lose weight. And on the other side, copper is actually picking up copper from the copper solution, so it's actually gaining in weight. So these are called technically active electrodes. They are literally part of the redox reaction themselves, as opposed to an inactive electrode, which basically is a conductive material that doesn't participate in the redox reaction. So here's an example of that. Here I have iron 2 plus going to iron 3 plus in oxidation, creating electrons. And so if you drop something that was conductive but didn't participate in the redox, and commonly we have conductive carbon or graphite or platinum, which is a very inert metal, then those electrons that are generated in the oxidation can actually be picked up by the electrode and carried off into the circuit without the electrode itself participating. That's called an inactive electrode. For general chemistry 2 applications, you'll predominantly focus on using graphite carbon or platinum metal. So just some other definitions. Now, where the oxidation has taken place, you're going to generate electrons, therefore that is negative. That's called an anode. And mnemonic I have for that is, look, an ox, an anode. So anode is associated with oxidation. And consequently, because it's releasing electrons, they're going to build up, so the charge on that is negative. And that might help you remember within the word anode, there's a little N hiding there to remind you of that. Then on the other side, you've got a red cat, which is a reminder that reduction takes place at the cathode. Because it's gaining electrons, that particular space is actually positive in nature. And just a reminder that if I look at that T as if it's a plus sign, it's kind of a mnemonic to remember the charge on it. So within that circuit, once you build up electrons and they're moving over here from anode across the circuit to the cathode, you can harvest the free energy out here in the circuit, so you can break in there and pick those electrons off and use it to run some sort of appliance. And last but not least, there's this other area that we haven't really talked about. Isn't really part of your redox chemistry, but it's really based on thermodynamics, and that is, hey, as this reaction goes on and I'm, for example, building up positive charge on this side, or I'm consuming positive charge on this side, I've got to somehow balance out the charge within the solution, or else the free energy wouldn't make sense, and the circuit would shut down. And that's what the salt bridge is. It's a highly concentrated salt solution that allows you to make up for the cations that are being consumed or the cations that are being produced in one solution or the other. So here's a picture. We're going to work on the cathode side for a second. And pay attention to this copper 2+ ion. If it's undergoing reduction, one of those is going to be consumed, right? And it turns into copper up on the electrode. Well, consequently, that would leave the solution with a buildup of negative ions that have to be counterbalanced. And so that's why sodium ions move into the solution to balance that out. And that's the necessity of the salt bridge. And usually these salt bridges are, supersaturated solutions. Sometimes you have them separated by a membrane that'll transfer the ions, or sometimes they're in gels. And there's just different configurations you can see. On the other side, where there's oxidation going on, then zinc is turning into zinc 2+, and that's going to go into the solution. So the solution is building up zinc 2+ ions, so we have to counterbalance that with some sort of negative ions. So sulfate, which is in the salt bridge, leaches into there. And it might help you to remember this, that anions in the salt bridge move towards the anode where oxidation has taken place, and cations in the salt bridge move towards the cathode. That's the source of the name for the anode and the cathode. So here's just kind of a battery with inactive electrodes, another example where it's all set up and running. And basically in this case you have graphite or carbon electrodes that conduct electricity. They pick up the electrons, but they themselves are not participating in the reaction. Alright, so the next part of this, studying the spontaneous side of things, the batteries, is there's a shorthand, a battery notation. It's important for you to learn. And so what this is going to be based on this exact same battery that we studied back here. And we're going to just show you how to set up the battery notation. So traditionally, the oxidation is set up on the left and the reduction is set up on the right. The single line within on the left-hand side just shows that the two species, the zinc solid and the zinc aqueous, are different phases. That's a single line. The double line separates the two half cells or half reactions. And then if nothing's specified in a standard cell, it's assumed, and this is at standard state, that the aqueous concentrations are 1 molar. So now we'll go and do this second battery that was set up with inactive electrodes, where remember we had a graphite electrodes in both sides. So the inert electrode is also specified. It happens to be a different state than the two electroactive species, so once again a solid line separates them. Now it's interesting though that permanganate ion and the H+, which were both part of the reaction, they're all in the same state. They're all aqueous. So we have electroactive species that are the same state, which is solid, liquid, gas, or aqueous. If they're the same, you just separate them by a comma. And then once again, these were all in solution, so they are the same state as separated by a comma. But the graphite electrode you dropped in there was a different state. It was solid, so you separate that with the single line. And then once again, the double line is what separates the two half cells from each other. Alright, so with that in mind, I'm going to give you a chance to practice on this. I want you to write half reactions, do a balanced overall equation, draw a diagram, depict the cell in a battery notation for a voltaic cell that has a 1/2 cell or 1/2 reaction where chrome 0 turns into chromium 3+. And on the other side, there's a silver bar that turns into a silver plus. And in between is a salt bridge with potassium nitrate as the salt in there. And what I'd like you to do, and I give this away, that measurements reveal that the chromium electrode is negative. In other words, that's where it's building up negative charge, so oxidation's taking place. So identify the anode, the cathode, the direction the electrons and ions will flow from the salt bridge, and the oxidant and the reductant. So now stop your video, try and get all these things into your diagrams and equations, and when you feel like you've got it done and you want to check your work, you can restart the video. Okay, so the half reactions for this are silver plus, it's gaining an electron, becoming silver, and that's reduction, so that must take place at the cathode. So this is called the oxidant. It drives reduction. So once again, the verb, it's undergoing reduction. The name of that is called an oxidant because it drives something else to go to reduction, but its name is called an oxidant. Or sometimes it's called an oxidizing agent. Okay, in the other half cell, there's chromium 0 that's going to chromium 3 plus. This is oxidation, so therefore it's the anode, negative in charge. It's called the reductant. That is the name. The verb, the action it undergoes, is oxidation. The balanced overall equation is, if you put those together and make sure you balance out electrons. Now this is good, a good example because it allows you to see that, look, even though up here it only took one electron, in order to show you that these two reactions happen together, the electrons that were part of this reduction had to come from this oxidation, and I can't create more electrons than are consumed, so I have to have 3 equivalents of silver to balance this out by electrons. Go to draw the cell. This is traditional, it doesn't have to be this way, but basically you tend to put oxidation on the left, reduction on the right. So you put the chromium bar over here. And then, this is instructive, if this is negative, it means it's building up electrons, so electrons are moving from anode to cathode. Then the other piece is, remember that cation tends to move towards the cathode and the anion tends to move towards the anode. And if you turn this back into battery notation, these two species, as you can see here, are actually different states. This is aqueous and solid, so you have to separate that by a bar. The double bar separates the half cells. In this case, the silver and silver plus are also in opposite states, so you draw it as such. So now we're going to work on reading kind of a standard reduction half cell potential. And these tables are used a lot in electrochemistry. They help you determine batteries. We're going to do a lot in the next video on these to actually put numbers on batteries and figure out their voltage that they generate. But for right now, I just want to get you a general introduction to reading these. They're sometimes called standard half cell potential tables, or sometimes they're called reduction half cell potentials. But the first thing I'd point out about the table is they're always laid out in terms of reduction. So with that in mind, you'll look that the way every one of these is laid out, you're gaining electrons and reducing to your product. Now, if I wanted to run it in reverse, I could. In other words, if I started off with lead solid and I ended up with lead 2 plus, that would generate 2 electrons. And as we'll learn in the forthcoming videos, that would just simply change the sign on the voltage that it takes for that to happen. But for now, I just want you to kind of be introduced to the first part of this table. The most powerful oxidants, those that undergo reductions easiest, are on the top left. So when I'm reading the table and I go to the very top left, which in this particular table, silver plus is the champion, that is the most powerful oxidant or oxidizing agent on the table. Or silver plus will go to silver, undergoing that reduction easier than anything else I have listed on this table. Conversely, the agents that favor undergoing oxidation are on the bottom right. So if I went to this particular table, the iron solid is the best reducing agent, or will undergo oxidation easier than any other species I have on this particular table. So that's really important to read. So now what do you do with that information, just in a really qualitative sense? Let's just say that you wanted to set up a battery and you just picked a couple couples off the table. For example, you want to use the iron 3-2 couple. So let's search this. This is another thing you want to look out for, this to be very careful, because look, here's an iron 2 plus, but it ends up going down to iron 0. But we're looking for iron 2 plus, there it is, from iron 3 plus. That's that couple. So So that is that particular species, and then we're going to compare it to a tin 2 plus tin couple. So now here's tin 4, but I'm looking for tin 2, and there it is. Tin 2 plus going to tin. So with that in mind, the question would be, okay, how will this set up in such a way that it's spontaneous without having to go and pull out my thermodynamic tables? You can very quickly do this. The red cat, reduction occurs at the cathode. So you want to find the species that undergoes reduction best. So my tin 2 is here below my iron 3 plus, so the ones that are higher and to the left undergo reduction easiest, so that is going to be the species that undergoes reduction. On the other hand, the species that undergo oxidation best are to the right and down. So the tin 0 going to tin 2 plus is actually the reaction that you want to run the anode. So this pattern, that things that are above and to the left will drive something to the right and below to oxidation, is always going to hold true in a manner that's spontaneous. And so this is what you look for a battery. So if I wanted, I could take copper 2 plus and use this couple to be the reduction that drives any oxidation, such as nickel solid going to nickel 2 plus. Or if I wanted to take copper 2 plus going to copper 1, that would also drive iron solid going to iron 2 plus, and you only have to be separated by one line. The difference here is the difference in voltage, and as we'll learn later when we really put numbers on this, that's because that creates a negative free energy. Okay, so let's practice. First off, is it possible that potassium permanganate is able to drive the oxidation in nickel? And secondly, if you have a silver chloride silver couple and you connect it with an iodide couple, who would be the cathode and who would be the anode in making a battery? Stop your video, see if you can answer these two questions. When you're ready, restart the video and check your work. So let's see how you did. The first question, yes, it is possible that potassium permanganate is able to drive the oxidation in nickel because the permanganate ion is actually above and to the left of the nickel solid ion, so this will run reduction over this being oxidized. Now I want to go back and just point something out too. In this particular case, this is an ionic compound, so the counter ion, the fact that it was potassium permanganate, doesn't really matter, although you have to be a little careful with that when it comes to something that's in a coordinate covalent complex. So the second question, let's assign the roles of silver chloride silver couple and the iodine iodide couple. So once again, the one that's going to undergo reduction is going to be farther to the left and up, so that's iodine. So therefore that's the cathode, because remember that's where reduction takes place. And that's going to drive an oxidation that is to the right below, which in this case is only a couple lines below. It's silver solid going to silver chloride. And once again, this really drives the point home, because if you look, there actually is a silver plus going to silver solid, which is actually the top reduction potential. But in the case of silver chloride, this is a coordinate covalent bond, so it changes the electrochemistry, so you have to be very specific with what you're talking about. And in this particular case, I probably should have specified that this was silver chloride solid, not in solution. And a lot of times you wouldn't, in general chemistry 1 and 2, know what coordinate covalent complexes are set up, so your instructor will help you a little bit, but I'm just kind of giving you a heads up for moving forward into inorganic chemistry that coordinate covalent complexes are different than ionic salts. And in this particular case, the electrochemistry changes in a significant way. Alright, so I hope that after this introduction you're familiar with all these concepts, and I hope it's helped you get started in electrochemistry. And I would encourage you to continue on with the rest of the videos that teach you the different parts about spontaneous and non-spontaneous reactions.